Okay, so aside from just taking our force and mass measurements in the lab, we can also use a simulation to help out with this. So if you're in Cami, you won't be able to use this hyperlink here. It won't detect because it's already kind of flattened out. But on the Schoology page for this lab, you should have a link there that'll take you to the simulation. It's called Spring Scales from Java Lab. So I'm going to switch over to that tab. It works basically the same way as what we've got in the lab. We have a spring scale. Scroll this down here. Okay, on one side it measures mass in kilograms, and on the other it measures newtons of force. We're going to be looking at the newtons side. So all you have to do is click these two check boxes for the mass and for the forces acting on this. So down at the bottom here, you'll see that this already has a mass hooked onto it. You can kind of grab it and fling it, and you can see the spring bounce back and forth. Okay, and you can see the forces acting here. So you've got the force from gravity and the gray arrow pulling down, and you've got this red arrow that's the spring trying to pull back against this. So if I try and kind of pull this down a little bit, you've got the spring really trying to fight back against what I'm pulling down here. Okay, and then when it levels out, that force of the spring should be equal to the force of the gravity, which is why we no longer have motion here. Okay, so right now we have a 0.5 kilogram mass. We can change the size of that mass to let's do 1.01 kilograms. This also gives you it in grams, but remember for our equation, force equals mass times acceleration, or the rearranged version where you have acceleration equals force divided by mass. We want to make sure that we have the mass in kilograms. Okay, so our force is given to us over here in newtons. Again, you're reading the gray arrow, although the red arrow should also have the same number if it's kind of stabilized and kind of balanced out. So the benefit of the simulation is that you don't have to go try and reading between the lines to figure out what the force is on the scale. So for weird answers like 7.15, that would be incredibly hard to read that force on the scale. So this will give us kind of a more accurate value than trying to read between the lines and say, well, okay, this is 0.2 and this is 0.4, so maybe it's somewhere in between here, or this is right at 7 and this is 7.2, so maybe it's like 7.1, maybe it's just straight up 7. This gives us an easier way to kind of figure that out. It also allows us to use all kinds of different mass values instead of just the ones that we have in the lab. I have like 7 different options. There's like a 10 gram, a 20 gram, a 50 gram, 100, a 200, a 500, and a 1,000, I think. So this gives us a couple different like weirder options where you can get in between and test a whole bunch of stuff. And either way, we should still get about the same acceleration that we get in the physical part of the lab. This just gives us a little bit of an easier way to test a whole bunch of different masses and get an accurate reading on the force immediately without having to try and, again, read between the lines. Okay. You can also change the limit of the spring scale. Okay, if you want to use like smaller masses. So let's say you're doing something like with 0.08 kilograms, where you have very little force going on here. If you do this on the 2.5 kilogram, it's like barely going to move at all. And it does read out the number for you, so it still gives you the same value, but it's a little bit tougher to see. Okay. You just have to be careful on these because if you get to a mass that's too big, you'll notice, that the force of gravity becomes too strong for the spring, and so it's just pulling it downwards, and you don't get an accurate reading past that point. So in the lab, we wouldn't be able to tell this has a force of 6.37 newtons. We just know that it passed the limit that the spring can handle. Okay, so you would use this just the same as what we're doing in the lab. So maybe, let's say I'm doing this 0.65 kilogram mass, and I've got a force of 6.37 newtons. I can go over to my document and mark that down. So let's switch back to this. So I say my mass, which is 0.65 kilograms. Let me get that Annoying. There we go. Okay, 0.65 kilograms, and the force of gravity pulling down on it is 6.37 newtons. So 6.37. So if I take my force of gravity divided by my mass, what I should get is the acceleration. So I can go plug that into a calculator. I just take 6.37 divided by 0.65. What I get is 9.8. Okay. Now, to give you an idea of whether you're doing this right or not, no matter what mass you pick, the acceleration of gravity is constant. If you have bigger mass, then you're going to have more force pulling on it, and if you have less mass, you're going to have less force pulling on it. But the acceleration from gravity comes out to be the same for every object on Earth. So we should be getting around 9.8 or so on each of these. Or if you're doing it physically in the lab, your answers might be coming out more around 10. It's kind of rounded up a little bit. Okay? So, whether you're doing this physically in the lab or with the simulation, your acceleration should come out to be pretty much the same each time, and that's a good sign that you're doing things right. Okay? It's a good way to kind of check your work. Okay, so you'll be doing 5 trials of different masses physically in the lab, and again, calculating it out like that. So taking your force divided by your mass. You'll be doing that for the simulation as well for 5 trials, and then you're good to go.